to our lessons, everyone. Dr. Tullis here, once again, picking up a conversation about Gibbs's free energy, most often called free energy, and with the abbreviation of G for Gibbs. The method used so far in determining whether a spontaneous reaction is occurring had us evaluate two quantities. Those would be both the delta S of the system and the delta S of the surroundings. And we know that it's very inconvenient, very difficult to measure entropy changes of surroundings. So J. Willard Gibbs, working in the late 1800s, made the following assertion, saying that the maximum non-pressure volume work available to do on a system, that's what Gibbs's free energy is a measure of, work. Well, it's a function of both enthalpy and entropy. And that relationship, here's our enthalpy, is a relationship relating enthalpy to temperature in Kelvin and entropy. So we have the enthalpy, or the heat of the reaction, minus T, so our Kelvin temperature, and S being the entropy, the dispersal of energy, all relate to the spontaneity of a reaction. So delta G, Gibbs's free energy, is a relationship between the two thermodynamic properties of enthalpy, which is heat, and entropy, which is the disorganization of the system. And when we look at the impossibility of measuring specific values, it's more convenient to talk about changes in value. So here's our equation. This is the one that you should know how to use and manipulate for those variables. That says at constant temperature, Gibbs's free energy, which is just free energy of a system, is related to the enthalpy change minus the product of the Kelvin temperature and the standard state of entropy. That's 1 atmosphere of pressure, 25 degrees Celsius, which is 298 Kelvin. That's our standard state conditions. So Gibbs's free energy is a relationship that will tell us if a reaction is spontaneous by looking at the enthalpy value and the entropy value and the temperature with which the reaction occurs. So let's put this together. The sign of delta G is what's important to us. Think of the delta G as really as a measure of the driving force of a reaction. The sign will indicate if a reaction is spontaneous or not. Now, if delta G is negative, so delta G is less than 0, the reaction is said to be spontaneous in the forward direction. Again, that's if delta G is less than 0. The reaction is spontaneous in the forward direction. So if I have a reaction, A plus B yields C plus D, and the standard Gibbs's free energy is negative, let's say 50 kilojoules per mole. That tells us that this reaction is spontaneous in the forward direction. It would be non-spontaneous in the reverse direction. If delta G is a positive number, so if delta G is greater than 0, the reaction is not spontaneous in that direction. So, for instance, if I were to look at A plus B yielding C plus D, so if we reversed this reaction, and so we're reading it in the opposite direction, delta G, of course, is a state function, so it would become a positive value, reading it in the reverse direction. So delta G would be positive 50. So, of course, this would be, the initial one is a spontaneous in the forward direction. This would be non-spontaneous. So A plus B yielding C plus D with a negative value shows us spontaneity. The negative sign on a delta G says that this reaction will be spontaneous in this direction. However, if so this is in our forward direction. If I flip this reaction, so I have C plus D yielding A plus B. Again, we flip delta G from a negative value to a positive value. So in this forward direction, it is telling us that this reaction be non-spontaneous. Now, if delta G is at 0, we have an equilibrium. So we have a forward and a reverse reaction occurring at the same rate. And I know equilibrium is our topic for the next 3 chapters, but we'll also be sprinkling it into this lesson as well. So a system that is in equilibrium has a forward and a reverse reaction occurring at the same time. So if I had A plus B in equilibrium with C plus D, so delta G is equal to 0. So delta G, again, is 0. If the delta G is negative in the forward direction, it is spontaneous. If it's negative in the forward direction, it will be positive in the reverse direction. Now, what are some conditions on enthalpy, heat, and entropy that are favorable to create spontaneous reactions? Well, the most favorable condition for heat is to have a negative enthalpy. Negative enthalpy tells us that it's exothermic. So for enthalpy to be less than 0, to have a negative delta H, which is exothermic, and having that negative delta H contributes to a negative delta G. So that's favorable. Another favorable variable is an increase in the entropy. So for S to be greater than 0, we want a positive entropy to contribute to a negative delta G. Now remember, that's because there's a negative sign here. The Kelvin temperature times a positive value of entropy is going to help contribute to this. So that is a favorable indication of a spontaneous reaction. Now that doesn't mean that those are the only ways we can have a spontaneous reaction. Delta H could be endothermic and still have a spontaneity reaction. Or we could have a negative entropy and still have a spontaneous reaction. So both play a role. Entropy and enthalpy must be utilized together to determine if delta G will indeed be negative or spontaneous. Positive is not spontaneous. Or if it's indeed 0, notice that there is a temperature dependence as well. So raising the temperature could affect the spontaneity of the reaction. I like this chart to help us predict whether the reaction will be spontaneous. So again, we're looking at our Gibbs free energy, and we want this to be a negative value for it to be spontaneous. So let's look and see different reaction scenarios here. So if we look at reaction number 1, and we have an exothermic reaction, that means that our delta H is negative. And this is a favorable trait, right, for our exothermic reaction to be a spontaneous reaction. So this is favorable to have that. And if we have a positive delta S, so again, more chaos and disorder in the system. So when our delta S being positive, then we are going to be spontaneous. We're going to have a spontaneous reaction here at all temperatures. So our delta G is negative, spontaneous. So let's look at scenario number 2. So we have an exothermic reaction. Again, this is favorable. We have a negative delta H. But let's say that we have a negative entropy. So this is unfavorable. So it's going to depend on, again, think if I have a negative value here, and I have a negative value for my S, remember, we need this delta G to be negative to be spontaneous. So it's going to depend on really the size of our delta H and the delta S. But at low temperatures, it still would be a spontaneous reaction. If you were to consider that this delta T, if it was a very low temperature, we can still have this reaction turn out to be a negative value. So let's say that we have for number 3, a reaction type, let's say we have an endothermic. So a positive delta H, and we have, this is unfavorable, right? But let's say that we have a positive delta S, so this is favorable. So again, it's going to depend on those values of enthalpy and entropy, but at a very high temperature, we can still manage to have a spontaneous reaction. And then we have number 4. Let's say that we have an endothermic reaction. Again, this is unfavorable. A negative delta S, again, unfavorable. And it doesn't matter what temperature that this is at, this is just not going to be a spontaneous reaction. This is just going to be non-spontaneous. There's just no way around it. There's no way with a positive value here and a negative value here, this temperature won't even make a difference. We won't be able to get a negative value for our delta G. Here's another tool chart looking at what we were just talking about, just kind of organized in a different way. So again, if I have my enthalpy, my delta H, that is greater than 0, so it's endothermic. And up here I have my enthalpy, delta H, that's less than 0, so it's negative, it's exothermic. Then over here, this shows me my increase in entropy, so I have my entropy that's a positive value, and a decrease in entropy, so my entropy in a negative value. So we know that having a negative enthalpy is favorable, and having a positive entropy is favorable. And so we know that delta G will be negative. It will be spontaneous at any temperature. At any temperature. We also know that having an endothermic reaction is unfavorable, and having a decrease in entropy is also unfavorable. So delta G is going to be positive and non-spontaneous at any temperature. We do know, though, that if we have a positive enthalpy and a positive entropy, we know that delta G could be spontaneous if it's at a high temperature, but it will be non-spontaneous if it's at a low temperature, so that delta G will be greater than 0. And so it is important to know that, yes, it is spontaneous, but it has to be at a high temperature. And same with, we know that this is favorable, having a negative enthalpy. Having a negative entropy is unfavorable. So we know that we still can get to that spontaneous point. It has to be at a very low temperature. So it is important to look at this chart and to memorize these different conditions and be able to apply them. Let's look at an example problem here and work through all of these different steps. So don't get so overwhelmed and take a minute. We're just going to do piece by piece. So let's calculate the standard entropy, delta S, of the reaction of the following at 25 degrees Celsius, which I'm just going to put right up here. 25 plus 273 would be 298 Kelvin. Using the data in this table, the standard enthalpy of the reaction is negative 633.1 kilojoules per mole. Okay, so let's look at this. We need to find our entropy of the reaction, which is the same as we can say the entropy of the system, right? Those words are identical. So we know that to find the delta S of the reaction, we need to find the sum of the entropy of the products and we're going to subtract the sum of the entropy of the reactants. So we're going to use this data over here, and we're going to look up C6H6 in liquid form, which gives us the delta S of 173.4. So we're going to do our products, which is 173.4. Remember, entropy is also in joules per Kelvin mole. So this is my product minus our reactant. So we've got C2H2, but we have 3 moles of it. So C2H2, we're going to do 3 times 200.9, again, joules per Kelvin mole. All right, so now let's do some calculator work. I'm going to do 173.4 minus, and I'm going to put in parentheses, 3 times 200.9. I should get negative 429.3 joules per Kelvin mole. And this is telling me that my entropy is negative. All right, so let's plug that in over here. This is my answer. Joules per Kelvin mole. All right, so let's move on to the next where it says calculate the standard Gibbs's free energy of the reaction. So we know that delta G, or the reaction, is equal to delta H, our enthalpy, minus T times delta S. And so, and we're given up here the delta H of the reaction. Now, we could have also figured out the delta H of the reaction, right? It's the same as finding our delta S of the reaction. We could do the sum of the products of enthalpy minus the sum of the reactants of enthalpy. We would get the same answer. But since we're given it already, let's just plug it in. And so we're going to go delta G of the reaction is equal to negative 633.1, and this is kilojoules per mole, minus the temperature, which was 298 Kelvin, times entropy. Now, remember, we found entropy to be in joules per Kelvin mole. So let's make it into kilojoules. So I'm just going to down here real quick, 429.3. This is joules per Kelvin mole. Now, we know that we got to have joules down here. We want kilojoules. There's 1,000 joules and 1 kilojoule. So this is going to be equal to 0.4293 negative kilojoules per mole. So we're going to plug that kilojoule, 0.4293 kilojoules per Kelvin mole. All right, so let's plug this into our calculator here. And I'm going to do negative 633.1 minus, and then in parentheses here, I'm going to do 298 times negative 0.4293. Close that parenthesis. We should get negative 505.2. 505.2, and this is in kilojoules per mole. So delta G for the reaction. And notice that we have a negative here. In delta G, if it is negative, that is spontaneous in the direction that it is written, in the forward direction. So we're able to, now if it was written in the reverse direction, that would be non-spontaneous. So we need to right in here, negative 505.2 kilojoules per mole. Let's look at another problem. We have a particular reaction. We're given the delta H, and we're given delta S. So we're given enthalpy and entropy. Calculate delta G for this reaction at 298 Kelvin. I'd like for you to pause the video and to work out this problem by yourself, and then come back and check your answer. So pause the video, and I will see you in a minute. All right, let's see how you did. If we use our equation, delta G, which is equal to H minus T delta S, let's plug in what we know. We know that our H is negative 238.4 kilojoules minus our T, which is 298 Kelvin, times, now delta S, it gives us our units as in joules per Kelvin. So let's change negative 80.0 joules per Kelvin. Remember, there's 1,000 joules in 1 kilojoule. So this would be back 1 to negative 0.080 kilojoules per Kelvin. So this is our delta S that we want to use. We need to have our matching units. So times negative 0.080 kilojoules per Kelvin mole. And now let's plug this into our calculator. And I have negative 238.4 times, I'm in a parenthesis, 298 Kelvin times a negative 0.08. Hold on, did something wrong here. Let's do this again. Negative 238.4 minus, in parentheses, 298 times negative 0.80. Oh, I missed a zero. That was it. 0.080. There we go. That looks better. So delta G is equal to negative 214.56 kilojoules. And let's see, let's round. We've got 4 sig figs, 3 sig figs. So we probably want to end with 3 sig figs, huh? So negative 215 kilojoules for delta G. And will this be spontaneous? Sure will be. We've got a negative delta G, so it is spontaneous as written. In the forward direction, it will be spontaneous reaction. And actually, I just went back to look at this problem. Since we're subtracting, we need to be significant to the 1 decimal place. So we would round that up to a 6. So it should be negative 214.6 kilojoules. All right. I made mention just a moment ago that since enthalpy, entropy, and Gibbs's free energy are all said to be state functions, which is a way of saying that they are independent of pathways that allows us to calculate delta G for a reaction, just as we did entropy and enthalpy by taking the sum of the Gibbs's free energy of products minus reactants. Calculating free energy from standard free energy of formations involves using that thermodynamic table that's found in our appendix. So again, this is another reaction, another type of state function that allows us to take the sum of the products minus the reactants. Let's look at another problem. Calculate the standard change in Gibbs's free energy for the following reaction at 25 degrees Celsius. Again, plus 273 would be 298 Kelvin. Delta G values can be found here. So why don't you pause again and see if you can solve for this, and then check back in and see if our work matches. To find delta G of the reaction, we're going to do the sum of Gibbs' free energy of products minus the sum of Gibbs' free energy for the reactants. So let's look at that. We're going to need to do the sum of our products, which is Al2O3 and Fe. But remember, similar to enthalpy, Gibbs' free energy for elements, single elements that are found in their natural state are 0. So we can just cross off, we don't even need to include iron or the aluminum. So iron from the products and the aluminum from the reactants. So let's set this up. We just need to have our Al2O3 minus the sum of our reactants. Again, we're leaving aluminum off because Gibbs' free energy for aluminum is 0. So minus the Fe2O3. So let's do this. Al2O3 Gibbs' free energy is negative 1582.3. That's kilojoules per mole. Minus Fe2O3, which is negative 742.2 kilojoules per mole. Let's plug this into our calculator. Negative 1582.3 minus negative 742.2. And I got negative 840.1. Kilojoules. So having a Gibbs' free energy of and having it be a negative is telling me that it is spontaneous in the direction that it was written. If this was a positive value, that would tell me it was non-spontaneous in that direction. But if we were to go in the reverse direction, it would be spontaneous. So you could tell me, because it's negative, it is spontaneous in the direction as written. It would also be non-spontaneous in the reverse reaction, because if we reverse that and we flip our equation here, then this delta G becomes a positive, and positive means non-spontaneous. So this was one way of finding delta G. We could do products minus reactants because we had those values. We also could find delta G by doing H minus TS. And by the H values we would use, we would need to do our products minus reactants for our enthalpy values. And to find our S, our entropy value, we would need to do products minus reactants for our entropy values. We have all of that data. You would get the same exact product. We just were able to use this kind of shorter way, a little less complicated. This is a little bit more work, right? Because we need to find the H value by doing products minus reactants for enthalpy, and then put that in for there, and then find the entropy value of products minus reactants of entropy. But it is still findable, and you would get the same answer. Here we're going to look at, so because delta G is a state function, just like delta H, and Hess's law, we can couple reactions together. So we have the decomposition of zinc sulfide. It is non-spontaneous. We can see that it is a positive delta G value. And this is used in industrial processes for production of zinc. So it's coupled with this reaction, sulfur plus oxygen, to create sulfur dioxide. That is a spontaneous reaction. So when we take two elementary reactions, so let's say I take zinc sulfide, ZnS, and it creates zinc and sulfur, and that delta G value is positive 201.3 kilojoules. And we take the second reaction of sulfur plus oxygen to create SO2, and that delta G value is negative 300.1. We can add these together, and notice that I have ZnS down here, Notice that sulfur and sulfur cancel each other out. One's on the right side of the arrow, one's on the left side of the arrow. So that is my target equation here. So therefore, I can take these two delta G values and I can add them together. So 201.3 plus negative 300, I would get a delta G of negative 98.8 kilojoules, which is a spontaneous reaction. So by doing this, this is coupling the reaction. So we're just adding when we need this to happen, but it's not a spontaneous reaction. We can couple it with a reaction that is spontaneous and largely spontaneous. Notice that it has a larger value than the non-spontaneous reaction is with the opposite sign. So we're able to get a negative free energy change that is then a spontaneous reaction. So by taking that same idea, let's look at this equation. When the oxide of a generic metal M, so this could be aluminum oxide, it could be potassium oxide, any metal. So they're just signifying the metal as M. So any generic metal is heated at 25 degrees, only a negligible amount of M is produced. So here's our metal oxide, and it is heated, and it is decomposing to make our metal and an oxygen. And this delta G is 289. So we have a positive delta G. That means that this is non-spontaneous. However, when this reaction is coupled to the conversion of graphite to carbon dioxide, it becomes spontaneous. So then it says down here, we're going to show that the reaction is in equilibrium, include physical states, and represent graphite as solid carbon. So we're going to say, so we have solid carbon. So the conversion of graphite to carbon dioxide. So I've got solid carbon turning into carbon dioxide. Now, I need something else on the left side of my equation. I've got carbon and carbon. I need oxygen on the left. So O2 gas. Okay, so let's figure out what this delta G is. And we can do that by looking down here at this data. We can do delta G as products over reactants. Again, remember this is delta H, delta G, delta S. So by looking at this, we can do, okay, my product is CO2, products minus reactants. Hey, look, both of my reactants are 0. So my delta G is negative 394.4 kilojoules per mole, right? We just took our product, CO2, minus the 2 reactants to get delta G. And that makes sense because this is a spontaneous reaction. So let's add these two together now. If I have my, so let's see what this reaction is going to give us. When I couple these reactions together, again, I've got elementary reaction number 1, elementary reaction number 2. Let's see what I get here. Well, notice that on both sides of the equation, I have O2 and O2. So we're going to just cancel those out. So that means that I'm going to have my metal oxide, that's in solid, plus my graphite carbon, and on the right side, I'm going to have my metal and carbon dioxide gas. All right, now let's figure out what that delta G is. Again, we're just going to add my delta G's from here. So I've got, we're just going to do this, add, or sum them up. So 289.2 plus negative 394.4. I should get negative 105.2 kilojoules. And that negative, that's telling me that now it has become a spontaneous reaction. Again, I just want to show you, how did we get that delta G? We weren't given that, right? When we wrote this second elementary reaction, we coupling it with the conversion of graphite to carbon dioxide. So I knew graphite, it told me graphite was solid carbon. It converted to carbon dioxide, and we go, oh, something's missing. Oh, carbon plus, we need oxygen on the left. Okay, so then to find that delta G, remember, is the sum of the G products minus the sum of G's reactants. And so my product was CO2. CO2 was negative 394.4. Products minus our reactants were 0. So delta G was negative 394.4 kilojoules per mole. This was for our second elementary reaction. All right, so let's use Hess's law to calculate delta G of the reaction. And so this is our target reaction. NO, nitrogen monoxide, plus oxygen, and it's just single oxygen, yields nitrogen dioxide. And we need to find that delta G. So for no other reason that because that it's just listed first, we need NO on the left. And if we look, NO, NO, hey, we've got NO and it's on the left. Okay, so I'm just going to rewrite, this is number 1, number 2, number 3. We're just going to rewrite this third equation because NO is on the left and there's one of them. We're just going to leave it as it is. So let's write NO plus O3 creates NO2 plus O2. And that delta G is negative 199.5. All right, next, let's look for O, because it's next. Let's just find O. That's O3, that's O2, O2, oh, there's O. So what I notice here is that this O is on the right side of the arrow. I want it on the left side of the arrow. So I need to flip this equation. Also, I notice that I have 2 and I want 1. So I need to take half, right? Half of 2 is 1. So I need to take half of everything in this reaction. So let's write this. We have, let's see, if I flip that, I'm going to have O converted to, and then this is going to be half of an O2. So then my delta G, again, I need to flip that and take half. So let's do plus 463.4 divided by 2, and we need to take the opposite of it. So that would be, let's plug it in, 463.4 divided by 2 should be negative 231.7. Now let's look for NO2 on the right. Okay, hey, good, we've got NO2 on the right, that's good. All right, last, I noticed that when I'm looking at this, so we think, hey, maybe we can just be done with 2 reactions. All right, but I've noticed that I have an O3 on the left that isn't going, there's nothing to cancel it out, and I don't have O3 in my target equation. So I need to, where do I find O3? O3 is right here. It's on the left. I'm going to need it on the right to cancel out. And also, I only have one O3. Here I have 2. So I need to flip this reaction and take half of it. So let's write that out. So 3 divided by 2 would be, we can just write 3 halves. O2 is then going to convert to half of 2 is 1. O3. Now we're going to take this delta G and we're going to, it was positive 489.6. We're going to take half of it and we're going to flip the sign. So let's do this. 489.6 divided by 2 is going to be negative 244.8. Now let's use Hess's law. Let's see what we have here. I've got O3 and O3 that are going to cancel out. I have 1 O2 plus half of an O2, so 1.5 O2s, and 3 halves O2, which is the same as 1.5 O2. So I can cross off all of my oxygens, and I'm left with NO plus O yields NO2. Let's just make sure. NO plus O yields NO2. Hooray! Okay, so all that means is that we're going to take the sum of all of these delta G's. So let's do that. Negative 199.5 plus, plus negative 231.7 plus negative 244.8. We should get negative delta G is equal to negative 676 kilojoules, which tells us that it's a spontaneous reaction thanks to that negative delta G. All right, our last slide for today is using standard free energies of formation to calculate delta G. So here I have mercury oxide, solid, it's yellow, and it is decomposing into mercury and oxygen. So it wants us to do two things here. A, it wants us to calculate delta G using A, the standard free energies of formation, okay, and B, the standard enthalpies of formation and standard entropies of formation. So we're going to find delta G two ways, and we know we can find delta G two ways. So first we're going to do our G for the reaction, which is our sum of our G products minus the sum of our G reactants. Gives us free energy of products minus reactants. Okay, so here's our, gives us free energy for our products, our Hg and half of an O. Hey, look, Hg and O are both 0. Minus our reactants, HgO is negative 58.43 kilojoules. So 0 minus a negative 58.43 gives me a positive 58.43 kilojoules. And because it's a positive, that tells me it is non-spontaneous. Okay, nice, short, and sweet. Now let's look at using our enthalpy of formations and entropies of formation to find delta G. So in this equation, we're going to use delta H minus T delta S. Okay, well, first we need to find delta H. So let's go over here. To find delta H, we need to find the sum of our products minus the sum of our reactants for enthalpy. So let's look at that. Well, we've got our products are both 0. So I can just do 0 minus our reactant is negative 90.46 negative 90.46. So 0 minus negative 90, we're going to have a delta H of positive 90.46 kilojoules. Okay, that gets us H. We know temperature. Temperature, we were told, where? Temperature at standard conditions. So that's at 298 Kelvin. Okay, so we got temperature, but now we need to find delta S. Delta S, we're going to, again, delta S products minus delta S reactants. Same way. So my products, I've got Hg, which is 75.9 plus, now my oxygen value, don't forget I have half of an oxygen value, so plus 1/2 of 205.2, that's my products, minus my reactant, which is HGO, minus 71.13. All right, let's plug this into our calculator. So I've got 75.9 plus, I'm going to do 0.5 times 205.2. My products minus 71.13. So my delta S is 107.37. Oh, this is joules, isn't it? Remember, our S is in joules, so this is joules. And when we plug it into this equation, it needs to be in kilojoules. So let's just convert from joules to kilojoules right now. Move our decimal point over 3 spots, so 0.10737 kilojoules. Okay, now we have all the pieces here. Let's plug it in. Our delta H we found was 90.46 kilojoules per mole. Minus our temp, 298 Kelvin, times our delta S, 0.10737. Let's see what we get here. 90.46 minus, I put in parentheses, 298 times 0.10737. And I get 58.46. Here, 58.43. Same thing. Delta G of the reaction is equal. Yet we did it. We found it 2 different ways. We could find delta G of our products minus reactants. We could find delta G of our enthalpy, which is enthalpy of our reactants minus our products, minus temperature times delta S. And remember, to find delta S is products minus reactants. This one was a bit more work because we had to find delta H, we had to find delta S, but we were given all of the information. So something to keep in mind. We can find it 2 different ways. We get the same answer. Obviously, this one is less work if you're given delta G's. If you're not given delta G, we can find delta G if we know enthalpies and entropies.